Hello, welcome to this course on Introduction to Big Data. This is part of the Data Science BSc program offered by IIT Madras, and this is an elective that's available to students interested to take more fundamental knowledge in how data is processed at very large scale. So I'm your instructor. My name is Rangarajan Vasudevan. You can find out more about me in the LinkedIn link that's provided below. In various parts of this course, we will be looking at different principles of big data and how it gets applied to very large scale processing as it pertains to data science, as it pertains to the aspect of data processing, which is usually the step ahead of data science. In week one, we'll be predominantly focused on principles of what governs big data. We will start off with understanding of what are the foundational paradigms of data processing at large scale, how does it vary from data processing at small scale, and emphasize on the technologies and tools lesser, but more on the fundamentals of how to think about such large-scale processing. So without too much ado, I think there is a lot of discussion that's happened already about big data in the broader market, especially now that the cloud has become extremely common. What we've seen is a variety of different descriptions of what big data constitutes. And the problem has been that popular media as well as the governments of the day have all caught on to it, and they all represent the notion of data and as well as artificial intelligence in very different ways, often attaching contexts which are not completely accurate. So before we go further into what this course actually does from a technical standpoint, we need to understand that there are going to be many different variations to what people mean by big data. So I'll start by giving my sense of what big data means to me. I don't mean to suggest that this is the only definition or the other definitions are not valid, but I feel that this particular way of looking at big data is quite useful when it comes to problems that require large-scale data processing in real life. So let's start by looking at what big data is not. First and foremost, I think the concept of big data was quite popularized recently over the last decade or so. But prior to that, there were multiple different companies which were doing their own innovation. They were also having at times open source projects which were dedicated towards giving access to these technologies to a larger market for free. And even before mainstream technology caught up to big data, there were these companies which were doing a lot of work in advancing it. I'm talking the likes of Yahoo at that stage. Google, of course, started off what was originally the foundational concept of big data itself, called as the distributed file system and MapReduce. We'll talk about those later in the lecture. And then, of course, you had also smaller companies, at that time, smaller companies, I should say, like LinkedIn and even Facebook, which was up and coming, who were using big data in a significant way. And they rallied together to create the initial days of progress. So it was only around 2010 and 11 that mainstream technology media caught up to it. And here's an example from one of the predominant analysts, companies that analyze technology landscape and report on what's new, what's hot, etc. There's a company called as Gartner. They did this definition of big data back in 2011. And they quantified the concept of big data as corresponding to four things. The first being volume, which refers to the bigness of big data. That's where the word big comes from, right? Or the connotation of big comes from. So here, as the name suggests, volume is directly a reflection of the quantity of data that's available to be analyzed. So terabytes, petabytes, all of those are important characteristics in this dimension. The second dimension is something they called as variety. Variety refers to the fact that data does not form a specific format, or does not come in a specific format all the time, whereas it comes in myriads of different formats. The more you seek data, the more you find that it's structured in completely different ways at its source. So while this seems not that big a deal right now, back in the day, around a decade ago, there were actually a lot of different ways in which data which was being produced was actually standardized, right? So it didn't matter which format the data was in. There were attempts at standardizing the data to fit what's called as the Excel sheet, spreadsheet format, which is a relational representation of data in rows and columns. Columns usually refer to multiple different data types or data elements, and rows usually refer to different records or different instances of that particular data entity. So as an example, if you looked at the world of customers, the customer data is usually represented in the form of multiple different types of customer information in columns. Like for instance, name is one column, date of birth is another column, address is a third column, etc. And then each customer would be a record, and each record will therefore be one row. So you can imagine all the list of customers arranged as rows, one after another. So in total, they form the spreadsheet kind of structure, or a matrix kind of structure, where each cell value represents the value of a data element for a specific customer. So at that time, despite data being of different types, since the predominant relational databases, or what's called as RDBMS or databases in general, did not support varied data formats, and in fact they predominantly supported and were optimized to query tabular data structures, or what's called as spreadsheet data structures. There were a lot of attempts at processing data of different formats to bring them into a standardized representation of structural data, which is structured as relational. And that was actually causing a lot of pain, because data sets, especially in the internet, which originated in the internet, did not have a easy representation in relational formats, whereas they were easily represented using other kinds of structured representations, like one of which is called as JSON, or JavaScript object notation. So JSON, for those who do not know, is actually the predominant object exchange format for everything related to the World Wide Web. So every time there is a REST API call, which is basically your HTTP call that your browser makes to a backend web server, the data that gets fetched from it is actually in a JSON format. So data which is natively generated at such a large scale had to be now converted to fit into RDBMS processing pipelines, and that was considered inflexible, that was considered a waste of time, and therefore one of the early technological advancements that big data came to the table with was you do not need to convert data into relational format in order to work with it. You could just play with it completely native to what it was originally structured as. Great, so that's variety. So that was the second dimension, which was important for what made big data different from traditional data that was being handled by databases. The third angle here was complexity. So here, complexity refers to the fact that the data could have variety of different characteristics which are representative of the source of the data, which did not form a neat standard way in which you could look at how the data is being produced. So if you take the example of time series data, so let's take, for instance, data that's being collected by a sensor that measures weather related parameters in your city. So let's take, for simplicity, just temperature and air pressure as an example. So a simple time series of this kind of data set could look like a timestamp, a temperature reading, and the current air pressure, right? So these three columns could be read every 5 seconds, as a result of which you could have data that just kept adding and adding over the course of the day, and over a period of time, let's say a year, this truly became very large in scale, so that it qualified as very large in volume. It's not really, that complex in terms of variety, because it's just three columns structured in an easy spreadsheet kind of a manner. But what if the data was not neatly spread out in terms of time periodicity of every 5 seconds? What if sometimes it's 10 seconds? What if sometimes the sensor goes without power for half an hour and then comes back up and sends a whole bunch of data corresponding to that half an hour within the same second, right? So if you look at these kinds of patterns by which real world data collection systems get impacted, there is a direct impact on how the data itself is actually collected and played. So in that kind of a setting, the data is actually going to be more complex than having a very clearly formed representation, and therefore you have to have mechanisms of dealing with it. So in the case of data having uneven periodicity, sometimes 5 seconds, sometimes 6 seconds, sometimes 7 seconds, sometimes maybe once in 10 minutes, you need to be able to deal with that, the fact that there are gaps in the data with respect to periodicity. For some applications it might matter, but for some applications, like for instance, if you wanted to report on average temperature every hour, if you didn't have data for 1 hour, what do you do then, right? What do you report? Do you report zero? Do you report null? Do you report the previous hour's temperature? Do you wait for the next hour's temperature and then do an average? I mean, variety of different things are there. All of those are complexities that you have to deal with. Sometimes you might not have data corresponding to the right sensor in the right column, and this could happen because something in the sensor is getting reset as a result of the electric short circuits or whatever, right? In which case temperature reading could come under pressure and vice versa. So what do you do about that? Sometimes units might change. So it's easy to pass off these kinds of issues as quality issues, but then if you formulate these as quality issues that need to be corrected, for instance, one of the common ways in which quality issues are getting corrected is by just dropping the data because it's bad quality. Then you might find that a lot of big data is not usable because it's got quality issues in some column or the other, and the moment you drop it, you've just lost so much richness. So there are very many different types of complexity related challenges that come in. Those need to be handled natively, and the ability of a big data system to handle this is much better than traditional databases at that particular point in time. Again, I'm talking a decade ago, right? Obviously things have evolved significantly since then, but let's again focus on what was defined at that particular point in time by this leading industry analyst, Gartner. The fourth dimension is velocity. Here, velocity refers to the fact that data comes into a data processing pipeline at a specific speed, right? So it's not about the rate at which data is getting generated at the source, which is something that's not under our control as a data processing engine, but it's the rate at which the data comes in from that source to our data processing engine. So think of it as the source, like this sensor example that we just spoke about, could be sitting on top of your local weather station. Now, if that sensor is just merely collecting the data and not doing anything about it, there is no need to process the data at the velocity at which the sensor is producing it. So if the sensor is reading and producing data every 5 seconds, and if all it's doing is just storing the data locally onto a hard disk, then you could write a data processing application which just picks up that hard disk once a day, let's say at the night, and processes the day's data once, and then publishes the data, and then the same thing happens the next day, night, etc. In which case, velocity is not that much of a problem at all, because you're doing what's called as batch processing. And even though the source is producing data once every 5 seconds, you are only collecting and processing the data once a day. So velocity is not a challenge. On the other hand, if your application which processes the data looks to collect the data as soon as it's produced, so this is what's called as streaming processing, and you want it to match that periodicity of the data production very, very close to reality, then you would want to build a system which looks at ingesting the data the moment 5 seconds are over, right? The moment that data is being recorded by that sensor. In which case, velocity is a challenge that you'll have to deal with. So let's take, for instance, the same problem statement spread across the scale of India. So we're talking about sensors in every single weather station, in every city, every town, every village, every district, and each of which is producing this weather collected data for every 5 seconds, and you're having to build a data processing pipeline which collects such a vast volume of data. We're talking tens of thousands of cities or data collection points every 5 seconds. So the frequency at which data is getting produced is on the order of thousands of hertz, meaning thousands of data points every second, and you have to process that in real time, because if you don't process that in real time, the next 5 seconds worth of data is already at your doorstep, and the next 5 seconds at your doorstep, etc. So the data just keeps piling up without actually waiting for you to finish processing, right? Because that's the reality of these very high velocity data applications. So how do you scale data processing to very high velocity is a intrinsic challenge for these kinds of streaming applications. So big data evolved to cater to these kinds of use cases as well. So for instance, one of the companies that did a lot of work in streaming way back then was Twitter, right? So the Twitter that we see today actually had very similar data processing challenges that it saw back then, and it actually open sourced a lot of data related streaming data processing related software to the world of big data. Great. So these are 4 examples of these are 4 dimensions of big data that Gartner used at that time to characterize what constituted a big data application. So I would say in today's day and world, I don't think any of this is really that relevant anymore, right? So in fact, if you remove the word complexity, what you see as the remaining 3 dimensions, all of their words start with the letter V. So back then it used to be common to think about big data as the 3 V's of data processing, like volume, variety, and velocity. And then Gartner added this complexity as the 4th thing. But in today's day and age, big data is not just about the 3 V's. There's so much more to big data than just these 3 V's. All right. Let's go to the next common misconception of what big data is about. Back in the day, again, big data, like I said, evolved using open source contributions, and almost all those open source contributions were under the Apache Software Foundation. And within the Apache Software Foundation, there were many different umbrella projects created, but there was one umbrella project that became extremely popular, and that was called as Apache Hadoop. And the word Hadoop comes from the inventor who took inspiration from this baby elephant that his son was playing with frequently. He was working with Yahoo, and Yahoo was very heavily inspired by its own data processing challenges, but also by this seminal paper, research paper that was published by Google, called as the Google file system, and MapReduce, which is the second paper So both these papers published within a couple of years of each other. This was during the mid to late 2000s. And Yahoo was heavily inspired, and they started to think about what does it mean to make that kind of technology be accessible for broader broader usage. So the fundamental understanding, or the motivation rather, that came from the Google papers was that can it be possible to run very large scale data processing applications that cater to those 3 V's that we just talked about using just pure commodity hardware. So what that meant was, can hardware be as simple as a regular motherboard with an x86 processor attached to it, with simple disks, hard disks that you can get from regular hardware stores, and string all of it together into a standard PC or desktop server or a simple enterprise server, and then put a whole bunch of those servers together, meaning put a cluster of those machines, like hundreds of thousands of them, to get to the scale and processing capability that you need to process very large amounts of data. Why was that problem important? Because during those days, the only other alternatives that you had to process very large data was heavy proprietary software, which had its own expense, which had its own proprietary hardware design as well. So I'm talking about the examples of clay supercomputers, which were extremely powerful and played a very significant role in what's called as high performance computing, mainly used in very high end scientific research, like understanding understanding the cosmos, understanding space, understanding nuclear fission and things like that, right? Or you had to pay very large amounts of money to proprietary database vendors like Oracle or Teradata or IBM. So there was nothing in between, and all these companies were clamoring for technologies which help solve very large data processing problems. And Google, for the first time, actually proved in reality that it's possible to actually string together thousands of these very cheap machines and run like large scale data processing on top of it. And when they did that, one of the first things that they noticed was that if you had a large number of small, very cheap machines, you had a very high degree of failure every now and then, right? And the failure could be failure of hard disk, failure of CPU, failure of motherboard, failure of variety of different things, networking cables, etc. So how do you design data processing pipelines which withstood failures and still continued to make progress, so that at the end of how much ever time that you allot to it, let's say a day or 2 days or a week, the task that you wanted done at large scale still got done. And that guarantee of continued progress in the face of failures was extremely important for large scale data processing. And that became basically built out into this technology called as Apache Hadoop. So initially Hadoop was just a collection of 2 very important pieces of technologies. One was the Hadoop file system, which mirrored the Google file system, and the second was the Hadoop MapReduce, which mirrored the Google MapReduce paper. Over a period of time, it became an umbrella project because a lot of associated technologies started to be built out to process data. Like for instance, SQL was a common query language for traditional relational databases like Postgres, MySQL, Oracle, etc. So the open source community built out an SQL layer on top of Hadoop, which was called as Hive, right? Then the ability to work with data processing in much simpler language or semantics was recognized by some of these same companies, even Yahoo for that matter. And so they built out a much simpler custom language for large scale data processing, which didn't require to know Java at enterprise scale, right? Which is what MapReduce required you to know. So these simpler languages were called in different shapes and forms. One of them was called as Pig Latin, and then there were other variants as well. Then the ability to collect data from the source became like a significant capability, because you still had to get the data from that sensor, like that sensor example. You had to get the data from that sensor, to a central cluster of machines which you could use to process the data, right? So those data collection agents had to be resilient to failures, had to be very large scale because they had to be deployed in multiple different sensor locations, etc. So that project came to be known as Apache Flume, etc., etc. So variety of different technologies, all of them were together batched under this Apache Hadoop umbrella project and became packaged together along with Hadoop, and that open source technology and the uptake of that was skyrocketing at the time of 2011 and 2012. So long story short, while Hadoop was the poster child of big data at that time, it no longer is. In fact, in today's day and world, I don't think anybody uses Hadoop with as much gusto as they did back in the day. In fact, today, the constituent projects within the big data landscape are so far and spread out that it's hard to put it under one umbrella anymore, right? So, therefore, big data is not about Hadoop anymore. Big data is not just about MapReduce or Hadoop. It's much, much more than that. The last thing I want to mention about what big data is not is, it's not about an architecture. So it's not about massively parallel processing. So what I mean by massively parallel processing is, remember I said that a cluster of machines, the machines each processing large scale data in such a way that even if there are failures of certain components, there is continued progress. That kind of an architecture is what's called as a massively parallel processing architecture. MPP is how it's acronymized. It's massive because the data set is large, but also the cluster is large, like thousands of machines we're talking about. It's parallel because each machine does its own thing without waiting for any other machine to be ready. And it's parallel because every single one of those machines makes progress and gets to a certain stage of completion without actually having dependencies on anybody else, right? And it's processing obviously because every single machine has the capability to process some portion of the data, if not all. So that kind of an MPP architecture has been common even before big data came into play. Like for instance, this supercomputing, or rather supercomputers built by Clay and the likes, or even before that, there were these attempts at harnessing the power of individual desktops that we all had sitting at home, which were not being utilized during the night time, etc. And there were projects which would harness this power to do some bit of work across the internet, right? And these projects were very popular back in the day. I'm talking during the .coms. So they were all early examples of MPP, much earlier than even big data was. So certainly big data did not invent the MPP architecture. And today, if you look at the world of how cloud has reshaped technology, certainly big data is not just about cloud either, right? It's not just about one specific architecture. It's much more than that. So with that, I'll pause. In the next lecture, we will look at what big data are really about and how does that shape the world of data science. And with that, I'll stop with this video.